Page number not the same.
The slides are equal. It's not 7 chapters, it's like the first lecture, second half, or something like that.
Oh, sorry. Okay, sorry. Let me read after. So different posts, right? Let me check. Something wrong. Oh, it's our previous slides. So this one, previously I learned how for the second part of chapter 0, sorry. And right now you have the slides, and the slides maybe different page number because I have the whole for the slides here. So you just find the same content. Don't care about the page number. Alright, so for this one, I just want to emphasize if we have exponential, and right now if we only have x follows time, time actually is the mean duration. The mean duration here later in maybe traffic theory we will have the possible physical meaning, time. And because of time, 1 over mean duration. So it's the rate. So we will have a rate associated with the Poisson lambda, specifically associated with a process we call Poisson process. Because Poisson process, then we will have inter-arrival time followed with exponential distribution. Alright, so exponential is an important one. Specifically, this one will be related to the later discussion talking about arrival process using the Poisson process. So this one, you should understand we will use it later. Well, as for the others, I think if we want to have an extension from a single variable to multiple random variable, this one. Still, we have probability density function, but this is the joint probability density function. To have the joint probability density function, how to have the way to define it? Because we have the relationship from CDF to PDF for a single random variable. And right now, we feel, okay, it can be extended from this way. So single one, right now we change it to multiple one. If we can have a multiple one, so we can have a relationship for joint PDF like this equation. If we want to do so, of course, we need to define joint CDF first. So here, this is joint CDF. Then joint CDF, initially we have a single random variable. And right now, we extend it to multiple ones. Multiple ones, same. Oh, for the first one, we need to have the probability lower than or equal to the specified value here. Alright, so conditions. Random variable lower than or equal to the specified value. Likewise for the n1, lower than or equal to n subscript n, subscript n. So this is the definition for joint CDF. If we can define a joint CDF for multiple random variable, then we can derive joint PDF. Well, maybe you have a question about CDF here. We can define joint. So this one still valid for the discrete random variable. Yes, but for discrete random variable, same. It will be necessary to have the definition for this one. We just have the direct definition. Oh, okay, same. If we want to have PML for a single random variable, it should be the probability equal to the specified value. And right now we have the extended version, so we have multiple specified value. Likewise, as random variable, same. We need to get the probability when it is equal to the specified value. Well, these are the associated function PMF, CDF, and DDF for the multiple random variable. Well, this one actually is the definition, and this one it is not definition. It says if we want to have the function here. Through derivation, actually we have this relationship. So this one it is not definition, but this one is definition. And this one is definition. Or maybe you think, okay, forget it. It's hard for us to have the other definition. You can treat. Oh, we can define. Or maybe we define for some reason. So it is not a definition actually, but we can define. Or PDF can follow the relationship to have this function. But normally actually I know the two equations here, they are definition for sure. But this one, it cannot be a definition, but we can use it to serve as a definition to derive joint EDF. Alright, so about the current description. Questions? I think it's an easy extension, so I go through this quickly. Actually, in the past, if we have a longer time to stay here, maybe you'll feel okay, it's so hard, so I go through quickly. If you still have some question, maybe you can look up some reference books, or maybe you can use Google to find some results. And that's what we point out the feature about independence and conditional probability. Conditional probability, this one. Conditional probability should have a form like this. This is actually to separate this one, this probability, and this probability. So, well, to have a condition, this one. Alright, so normally we should have the form event A given the condition B, and this form is the conditional probability. If we can define conditional probability, then we can define independence. So independence actually talking about this, right? Even I have a condition under condition B, but it's irrelevant to the condition. So still we have the original probability A. If so, how to define conditional probability? Conditional probability actually follow the form here. For event A probability for this one, because we have a condition. So we should consider the joint. Actually the intersection of this condition. So under the condition, how to do? We observe A, so under condition, we have an intersection. Then we have this way to observe the current event. So if we have a event that one here, it's A and it's B. And this is the universal set. In fact, we should pass on the universal universal set to observe the original probability without any condition. But right now, because we under this condition, so we should have a new universal set. Not U. We need to change it. Oh, it's under condition B. So here A and B. So we consider the interaction. Consider the interaction, and then what is the portion? A area, the portion from this area A into the interaction, and then we can define the conditional probability. Well, if we can define the conditional probability, that says this one, and so that it says equal to A. So we will have sorry, something wrong. This one should be A under condition B. Alright, and this one it should be B, under condition B. So here, under condition B, so we should have this. And under condition B, so sorry, I have the correction. Universal set U, change it to B. Alright, so we have these. And if we have this after correcting version, so we will have joint probability equal to A and B. Alright. If a joint probability equal to A and B, we have the probability. But in terms of the current distribution, something like here, look at this. If this one, I have a notation B. Alright, so where we have B, this one. And if I have a notation A, then here we have A. So A, comma B, that says it's A. Alright, and this one, it's B. Okay, so in fact we follow the previous notation. So about the current distribution, we should have the distribution like this, A and B. So we have the joint and the new universal set because we have condition. So under this one, so the universal set change it to B. And likewise for this, you can have A and you can have B. Here A and B, and this one is B. Alright. So if we have all these and define so-called here it's the conditional probability in terms of something like we want to pass on PMF, even it's not PMF, and this one something like pass on CDF to have some distribution. But currently it is not PMF, it is not CDF, but we want to have the derivation. Oh, okay. If I want to discuss the probability here, so how to have the probability actually this way. And you just change comma to indicate and so it's easy to have the derivation. If we have the previous notation pass on event A and event B to derive the conditional probability for this. And so that, yeah, it's true. We still follow the same concept. Well, so this is the conditional probability, and the conditional probability allows us to have the possible derivation. So the derivation here, you can understand for sure. But one problem, if we have the independence, so previously, in fact, I already have the relationship independence. Independence here, A under condition B equal to A. So we have this joint probability equal to A and B. And how to have the interpretation? Look at this. If we have this, something like right now we have S1 and S2. If we have this, what it means? It says it should be the individual one. Is it okay? I don't know. Come current description enable this one. Right. And how about this one? Is it okay to extend to n larger than 3? Actually, it doesn't mean independence. This one ensures independence, but independence actually through the other possible discussion, we can have the result. Oh, okay, if we have the joint probability, actually the joint probability should follow the product form. So, how to have the possible condition independence, of course, imply this. But how to guarantee independence? It should be a pair of variables follow the product form. 3 of them follow the product form, so n of them follow the product form, then we can guarantee independence. But for this one, I just mentioned here directly. I mentioned the result if we have independence. Yes, we should have the product form. Because of the product form, actually you can check. Yeah, it's true for this version, something like this version. CDM version. So the CDM should have the product form as well if we have the given result independence. Well, so this page I already have the results if we have a conditional probability using the current form, and so that it will be easier to tell how to have the expression of the variations. And actually for independence, we should start from two events. Actually, if we want to extend to multiple events, current result, it doesn't mean we can guarantee independence. We should have a pair, 3 of events, 4 of events, 2 ends of an event. All of them should follow the product form, and then we can use them to guarantee independence. But independence can imply this one for sure. Of course, can imply the pair and can apply the product form for 3 events as well. Well, about the current page, okay for you? So I actually made it okay, so let me continue. So for this one, actually, it's past theory. Past theory actually is a fundamental theory for the extended theory. For example, even for machine learning, sometimes we need to pass on this. Well, if we want to check past theory, so what it means, if we have the conditional probability. For the conditional probability, something like, oh, given this condition, and we have the outcome. So we have the condition, we have the outcome. But right now we want to change it. We don't want to have the outcome, but actually we want to know, okay, right now, if we have the observed outcome, can you tell? Oh, okay, because of y, so that we have the outcome, so we want to find this. If we want to do so, while we have the relationship, it says, oh, if I want to change the form, so we want to have the rewrite for this one. To rewrite for this, we should have this, right? So currently, y and y, correct. And to write that one, so we have x and y. But change it to this one, so we can have the position change it to y and x. And y and x actually, you can consider, oh, okay, this one actually y under condition x. But we want to remove x, so you just multiply the probability of x. So that's why we can rewrite the current one to the form. To the form here, in fact, we want to have the different concept. This concept, given this condition, then we can trigger the output. And the current one actually wants to reverse it. Is it possible to have the observed outcome first, and then we want to find the reason reason comes from why. Of course, we can change it to the reiteration, then we can change it to this one. But y and y same. This one should be multiply p of x. And so that we can change the curve derivation. Given that condition, because of the reason, then we can have the outcome. Can we have a different way to calculate the probability? If yes, it's yes. So we have for this one as theorem. And by theorem, then you may have a question. Only the curve form. Maybe we can have the further derivation. Alright, so for this one, it's okay. We have for the new form to get the numerator. But for the denominator, y. Okay, to find y, is it possible to have a new form to derive that one? Say yes, we can have the summation. And here, similarly, we have xi. What that means if we have a y, actually we can have a partition. Okay, it's y here. We can have a partition. So we have x, we have x and we have 1, 2, 3, 4 to the others. We have a universal set u. Alright, so we can find partition xi and xi sub. We don't have the whole area for xi, but if we want to have the union for all xi, then we want to have the universal set. So we can have all the possible partition so that y can be expressed in terms of the current form. If we can express this to the current form, actually, maybe you have a question. If we have this partition, try to find some reason, for example, x by y, by currently y, we have if I erase this, therefore we can redefine by finding the partition xi. So we should slightly change the current one to this. Okay, if xi actually, I choose 1, maybe it's I, correct? But we have this probability. And so that we have a form here. Okay, so for I and y under condition, under the outcome xi. And likewise for this, the numerator is I. Alright, so if we can rewrite so that we can have the minimal expression, we just want to know, given the outcome, we want to find this y. Okay, likewise for this. Sorry, maybe something wrong. Let me think about this. It's correct, no problem. Alright, so we have the new form. Okay, so these one actually under the observed one, xi, so it's true for these. But for y, actually we can have a partition. So let me think. Even the notation is correct, but we need to have the interpretation. The interpretation says, okay, we have the outcome. Okay, let me rewrite. Even the notation is correct. So let me have a figure first. So let me erase all. So I feel something wrong, sorry. So we have a universal set. And right now for this, we have have outcome X.
So
Let me have a notation for this. I change it to, it should be something like this. Oh. So actually the current Venn diagram is correct, but right now it should be X or Y to sum as a partition. I'm thinking about this. It should be this. Let me think, is it correct? So if I rearrange it, so is it correct to have this? So currently, so we have something like this. Right now, the form should be well, for the row here, maybe I give side somewhat strange. So maybe still follow my first one. Let me think about this. As I have the inappropriate notation for I here or I here, but actually it should follow this one. But I have the wrong interpretation. Sorry. If I follow the notation, indeed, it should be something like this. Something like this, and so it will be easier to have for this one. Why to have for the partition? And so here it should be this one. Probability for this. And this one actually is a summation. Okay, so if we have the derivation, the form should be something like this. Alright, so maybe I should change the interpretation for this one. If we have this one as some I given condition y, but right now we want to change it to the new form. If we have this come from this, so maybe previously I have for the incorporate interpretation. The interpretation part should be this. I want to find this. Alright, and finally we want to change to this. Okay, so something like here, I have the wrong interpretation. So example, we have for some reason, find someone dead. So death here, because of the reason here. Alright, because of the reason here. But right now we want to reverse it so that, because of the reason, the ith reason. And so that we have the outcome F. So this is the outcome. And this is the outcome. It's all that is correct. So let me redescribe this problem. For batch theorem, after which you have the result. Oh, okay, if we have the outcome serving as a given condition, right? The outcome serving as a given condition. We want to find the reason why we have, if we have the outcome, is it possible to find the reason coming from this ith reason? If we want to find this reason, we can reverse the direction. Oh, we can have a test. The test here calls the outcome. Oh, for example, cancer. Cancer causes death. Maybe a lot of reasons cause this. So we want to find cancer only, or the other reason cause the death. So possibly it's cancer, the others cause death. And we have a lot of reasons. So a lot of reasons, this one causes death, that one causes death, all cause death. We want to put them together to have the ratio. And this ratio then says, oh, someone dies, and then find a reason. What is the probability for that reason? Okay, so this is the correct version. In fact, I go through this one. About the notation should be this one. Initially, I have the correct notation, but something wrong. Why is something wrong? Because of a wrong interpretation. Previously, initially I have outcome here, no. Outcome serving as a condition, but reason here. Alright, so we reverse this one. Alright, so this is the path theorem. For path theorem, it can be applied to the other field, but not the current field. So we mentioned this one for short description. After that one, we was maybe we will go to the other part, not the extension of the path theorem. Alright, about path theorem. Any questions? So let me highlight again. Notation, nothing wrong, but interpretation initially should be corrected to the current one. Alright, we have the outcome, then we find the reason. Alright, so if you want to apply this, you should have some background like this, and you will apply path theorem. Alright, so this is path theorem, but we won't apply it. And next one, we're going to have the property. Property talking about random variable. So then we care about how to derive the expected value. So we have a property about expected value. And property, so we will have the property. Actually, the property will hold for sure. So is it true? And right now we have the linear combination for multiple random variable. Linear combination for multiple random variable. And then can we have this result? Oh, it's a linear combination for all expected values. Right? So we have the first property. But for the first property, maybe you don't have the idea how to extend. So I rather have the idea. Firstly, we have the extension about the joint CDL. EML, EDL. And of course, we don't have the extension for this one. Actually, it's not this one, it's a function, for example, g. So if we have a function, g in terms of 1, 2, 3 to Sn, we want to find the expected value with respect to this function. So how to have the function? This is the extension. Oh, okay, we have the multiple interval. We have a g here. And we have this is if I use continuous one. Continuous random variable, so we have these. The join PDF. Alright, so this one I just want to have the extension. We can have the extension for join CDM, join PML, and join PM. How about to have the extension to the expected value? If we have a given function, it's a multiple random variables. So how to have the generation? The current function here, same. And previously we have a single PDF, a PDF for a single random variable. Right now we should extend to multiple random variables. So we have join PDF. And join PDF, of course, we have multiple integrals. And multiple integrals, and then you can have the result. If I consider continuous one, and for discrete one, actually similar one, but I use a continuous one to serve as a demonstration how we have the property. If we have this relationship, you can check yes. Follow the relationship like this, then you can have the property. Right. And for this one, you can try. Is it okay to have the generalized relationship and so that we can have the result? Linear combination of variables and find the expectation. So that the result should be, it should be the linear combination of all expected values. Alright, so if we have this extension, so let me highlight the extension. We should have an extension. Once we have the extension, so they will know, okay, it's a function of a multiple random variable. So how to derive this one? If we based on this relationship to the right, yes, it's true, we will have this. And finally, maybe you have a question. Maybe you have a question here. Single integral, it should be Si, and a single random variable, Si. And right now, how about if we have the multiple one? So same, a single one. Actually, for example, we have an integral. It's 1 and to I and to n. Still, we have I only. But we have x1 to n, so to I, and then to n. And so that we have dx1, dx2 to dxn. So it should be have a form like this. And right now you have a question. If we have the relationship in terms of joint PDF, can this one reduce to this? The answer is yes. It says variable here, it's I, right? If look at this, it's first one, I not equal to the first one. For the first one, actually, for this one, actually is the total of B. So we can reduce 1, 2, and 5 to index I simply. So this one indeed can be reduced to this one, even we derive the results using multiple random variable by using the joint PDF. So this one actually you can refer to our video so that you can check this one is true. But I want to let you know actually it's true even if it is not powerful, but still this one is correct. Alright. So if we have the new way to express the expected value for multiple random variable using the first equation serving as the definition to derive this, then we have this. And the second result, actually I just want to that you feel. Okay, if we have the new definition can enable the previous definition for a single variable. The answer is yes. I do not have the detailed version to make sure for you. If you want to make sure that one, you can do that for yourself. So let me start here. We have the sum of the expected value, this one. If we have the linear combination, then we have the linear combination regarding the expected value. As for the next one, next time I can let you know. Alright, let me start here. Before you go, let me check any questions. Alright, so for some you need to check by yourself. So you can check our video, which one you need to check it for details. Alright, that's all. If no further question, that's for your day and see you next week. Bye bye.
哎，等我一下。